Lesson has to do with dividing polynomials, and before we do so, let's look at a theorem that is going to help us with this idea. And for every a and b and c belonging to the set of real numbers where c is not 0, a plus b divided by c, you would like to say, is equal to, Glenn? A over c plus b over c. Notice that it is plus b over c, okay? And let's see if we can't prove this. The proof is actually very straightforward, very simple, in which here is our statement and the reason for that statement. And let's start out here with a plus b over c. And look at that and say to ourselves, that may be written as a plus b times, and we may write it as times Don
1 over c.
1 over c. And the reason for this, of course, is, Don?
Distributive function.
Well, not quite. But rather we are looking at, Doug?
The relationship between multiplication and division.
Right. We are then looking at the relationship between what? Between multiplication and division. Now, Don, looking here at the right-hand side, we have a plus b times 1 over c, in which we then may think of that as a times 1 over c plus, and then
B
Don,
times 1 over c.
b times 1 over c, and of course the reason for that is this is our distributive axiom, okay? And now looking at that, certainly a times 1 over c may be written as, what, Tim?
A over c
A over c
plus b over c.
plus b over c. And again, this is our relationship between multiplication and division. And we're done. Is that right? A very straightforward little theorem which enables us to work with some division. Well, in fact, from that theorem, I think we can then go ahead and look at a number of examples. Suppose we had a situation, let me just take the number 42 over 5. And you and I have been calling numbers like this, what? We have called these, what kind of a number is 42 fifths? And this, Doug, is a what kind?
ratio?
Yes, we think of this as a ratio, but what kind of a number did we call this as we were going through our number system? Well, certainly this is a rational number, isn't that right? A rational number. And once we then think of that as a rational number, let's then look at an expression such as, let's say 3x cubed plus 6x squared minus 9x divided by 3x. And if this one is called a rational number, what do you think you might like to call this expression, Glenn?
A rational algebraic expression.
Good, a rational algebraic expression, or simply, let's just use the phrase, a rational expression, all right? A rational expression. Now, when we look at a number such as 42 over 5, I think perhaps you wouldn't go through all of these steps, but you may think of this as 40 plus 2 over 5, and then relying on the theorem that we have just proven, we have there 40 over 5 plus 2 over 5, and of course 40 over 5 is 8 plus 2 over 5, which we normally write as what we call the mixed numeral of 8 and 2 fifths. Is that right? Now, let's then carry through using our same theorem in this rational expression. Without putting in this extra step, 3x cubed divided by 3x has a simpler name, Tom, of
x squared.
There is an x squared plus 6x squared divided by 3x is
2x.
We have there 2x minus
3.
what? Minus 3. Is that right? And notice here we have a polynomial, which happens to be a trinomial, divided by a monomial. Is that right? And in our numerical expression here we have 42 divided by simply a one-digit numeral. Well, let's extend that idea and look at something such as this. And suppose we had, let's say 4639 divided by 12. This number here is a rational number, certainly, and what we are now interested in is finding what this quotient is equal to. And remember how you then set that up in terms of what we think of as our division algorithm, all right? And let me just call this our division algorithm. A-L-G-O-R-I-T-H-M. Now, an algorithm is simply a procedure, a repetitive procedure by which we can in this case, simplify this number. Well, if this is our case of a numerical situation, what I'd like to do is to come over here and do an analogous case that perhaps has to do with one of these rational expressions. Suppose we were to look at, say, 6x cubed minus 11x squared plus 15x plus 1, all divided by, say, 3x minus 1. Now notice in this case we're dividing by a binomial, a polynomial which is other than a monomial in this case, all right? Well, similarly, what we would like to do is to set up a division algorithm in such a way that we would like to perform this long division. Let's think of this in terms of long division, okay? Let's come back here to our numerical case and proceed as we do with our long division. 12 into 46, we say, goes, what? Three times, because 3 times 12 is 36, all right? And then we would like to take the difference. Well, let's then come over here to our algebraic case, in which let's think in terms of 3x divided into 6x cubed will go, what? 2x squared, because 2x squared times 3x is 6x cubed. And we still have here then 2x squared times a negative 1 is a minus 2x, what? 2x squared. All right, and now what we'd like to do is to take the difference. Well, let's then come back here to our numerical case. And when we take the difference, we have 36 from 46 is,
10.
what? 10. And then we would like to bring down our next term, in this case the number 3. Well, let's then proceed in exactly the same way here. When we take the difference, we have 0. And then when we take the difference, we have a negative 9x squared. And then we'll bring down our next term here of 15x. All right, now let's then do the analogous case over here. And now we'd like to divide 12 into 103. And that goes how many times?
8.
That goes 8, is that right? And so 8 times 12 is 96. And then we'd like to take the difference. Again, let's then come back over here to our algebraic case. 3x into a negative 9x squared goes negative 3x, because negative 3x times 3x is a negative 9x squared. A negative 3x times a negative 1 is plus 3x. Again, what we'd like to do is to subtract. Let's come back here to our arithmetic case. 96 from 103 is 7, and then we'll bring down our next term of 79. 12 into 79 then goes how many times? 6, and 6 times 12 is 72. And now when we subtract, we have a number which is 7. And notice that this is our remainder, which is less than our divisor. Is that right? 7 is certainly less than 12. Well, let's then continue our procedure here. When we subtract 3x from 15x goes, what? 12x, and then bring down your next term, which is plus 1. Again, we'll divide 3x into 12x goes,
4.
what? Plus 4, and 4 times 3x then is 12x. 4 times a negative 1 is minus 4. And now when we subtract here, we have the number which is 5. Now notice that this is a polynomial of degree 0. Isn't that right? And this then is a polynomial of degree 1. And when the remainder is of degree less than that of our divisor, then in fact our algorithm is completed. Okay? Now, notice then, if we were to come back here to our numerical case, 4639 divided by 12 then is going to be equal to 386 plus, and then we may think in this in terms of 7 twelfths. Is that right? So we then may write our rational expression as being equal to, and here we have 2x squared minus 3x plus 4, and then we have plus our remainder here of what? We may think of this as 5 over 3x minus 1. Is that right? Now, let's then again continue with this. Looking at our numerical case, we then may conclude that 4639 is going to be equal to, and what may we say? It's what? 12 times, what number? 386 plus, and now here we have a remainder of 7, all right? And so in the algebraic case, therefore we may conclude that 6x cubed minus 11x squared plus 15x plus 1 then is going to be equal to this divisor, which is 3x minus 1, times this quotient of 2x squared minus 3x plus 4, and then a remainder of what? A remainder of 5. Okay? And this division algorithm, I think you will find to be quite important as you try to simplify some of your expressions. Let's look at another example in which suppose we had a case such as a cubed minus b cubed all divided by a minus b. And in fact, this is similar. We have already factored a cubed minus b cubed, and I think that this is simply going to reinforce what we have already learned. Now, I'm also doing this for another reason, in that when we have our polynomials, in this case a cubed minus b cubed, we have to think in terms of the coefficient, say, of a squared to be 0. Is that right? And the coefficient of a to the 1 power is also 0. And then over here somewhere, let me write minus a b cubed in order to be able to have room, so to speak, for everything that must come in here. And let's see exactly what we mean by that. A into a cubed goes what? A squared, because a squared times a is a cubed minus a squared b. Let me write it that way. Such that when we subtract, notice you're subtracting it from 0, which I'm simply leaving blank. We have there positive a squared, and then when you bring it down your next term, which is 0. And now a into a squared b is what? Plus ab. Is that right? Because ab times a is a squared b. And now ab times the opposite of b is a minus ab squared. And now when we subtract, we have 0 here. And when we subtract this number from 0, we'll have simply ab squared. And now let's then bring down our next term of a minus b cubed. A into ab squared goes
B squared.
plus b squared, because b squared times a is ab squared minus b squared times b is b cubed, and lo and behold, the remainder is 0. Now, when the remainder is 0, I think you will agree that we can conclude that this divisor is in fact a factor. Is that right? So then this may be written as what? This is equal to a squared plus ab plus b squared plus 0 as a remainder. Now let's see, I think I have room in here. Therefore, we may say that a cubed minus b cubed is then going to be equal to, in this case, a minus b times, and our other factor is what? A squared plus ab plus b squared, and sure enough, this is one of our factors that we are familiar with. Okay? Well, let me give you your homework assignment, and I think that's all that we need to do for today. This